So when you're calculating it on the test, I will calculate it with the other data points to see if that's the value that was achieved. So I do give a bit of a range, but those are the data points I would recommend that you use.
For sure, yeah. I just made note of that. So like in the test, I can use these numbers around approximately these numbers.
Yeah, exactly. How's everyone else this morning?
Doing good.
Sean, there's probably no more snowmobiling. Do you fish?
I don't fish actually, but I'm getting my quad working so I can make that work.
Oh, okay. So you quad. Oh, you have all the toys.
Well, yeah, I got some toys.
That's okay. Everyone needs toys.
Yes. Well, boys love their toys, right?
Yeah. I have a mountain bike. That's my toy.
Yeah, I got one too actually. I find that's a lot of fun.
Yeah, it is.
Yeah, going to Falcon Lake, especially I worked there last fall. I brought my bike with me so that whenever I got off work, I could go do the trails and stuff. That was a lot of fun.
Oh, nice.
Good perk of being out there.
Yeah, exactly. Did we lose Fabian? Doesn't Fabian fishes? Does he quad and snowmobile too?
I know he snowmobiles. I don't know about quadding.
Anyone else? Quad or snowmobile? Our family stays away from quads. We just flip them. We're not very good drivers of them. And it's funny because I grew up in the north and you would think I would know how to drive a quad and I have no idea.
It's really easy. It's not that bad. Just don't turn
Yeah.
too hard.
Yeah, I think that was my problem. I used to do a lot of like flood response work, and so we would have those side by sides. But I would just have someone else drive this side by side, and I would do the observing.
I mean, that works too. It's always nice to have a chauffeur.
Yeah, pretty well. That's what they were. And they would unload and load the quads because we would start, say, by the 430 bridge or whatever, and then we would go down to the 248 bridge. And so, yeah, they were kind of like my chauffeur. Well, we'll give everyone a few minutes. I'll try not to take too much of your time this morning. Well, I guess it is 9:06. Okay. I'm not going to spend tons and tons of time going over this PowerPoint presentation. I'll just highlight the important points for you guys. So this is, I guess it would be your module 9, which would be chapter, it probably shows up in your course notes as chapter 10B. I just refer to it as the external loads module. So external loads, the purpose or the reason why we need to calculate external loads is we need to determine or calculate what the increase in vertical stress would be in a soil mass due to a load that is being applied. So it could be a point load, so a concentrated load. It could be a line load, so it could represent an embankment or a railway. It could be a load from a foundation, so it could be circular, it could be square, and it could be rectangular in shape. So there's different types of loads we apply, and there's different shapes of loads that we apply. But we have to know what the increase in vertical stress would be at a certain depth in a soil mass because of this applied load. So that's why we have to have the ability to calculate external loads or the increase in our effective vertical stress. I know this chapter goes through the concentrated load, so the Boussinesq equation. It also goes through line loads. So you guys can work your way through those examples. Really in this course, what we're going to concentrate on is the approximate method and also the influence coefficient method. So those are the two methods that we're going to concentrate on in this course. So that's what I'm going to work on with you guys today, because this is the skill set I really need you to take forward so that you can do the next chapter, which would be calculating settlements in either a sand or a clay material. So do work your way through the other example problems, and if you do have questions on them, I'm more than happy to answer them, but that's not what I'm going to focus on today. So the approximate method is a method. It's a really quick and dirty method, so it's something that you can do in the field if you want to calculate what the increase in your vertical stress would be at a depth in a soil method, or sorry, in a soil mass. So the approximate method is also referred to as the 2-to-1 method or the 63-degree method. So those of you that have experience with surveying, 2-to-1 doesn't refer to 2 horizontal to 1 vertical. You'll note that it's 2 vertical to 1 horizontal. So it's the inverse of what you would expect when you're doing survey work. So it actually represents a 63-degree angle and not a 27-degree angle. So, so stress with the approximate method, we assume that the stress is distributed over a large area and that area of influence increases with depth. So the angle of spreading out is 63 degrees and it follows this 2 vertical to 1 horizontal slope. So if you take a look here, this would be a shallow foundations as an example, and it has a width B. And if we wanted to look at what the increase in vertical stress would be at a depth of Z, the width of our foundation increases at this depth Z by, it's the width of the foundation plus that depth Z. So that's how you would determine the width of your new foundation area. So if you wanted to determine what your stress would be at that depth of Z, or the increase in vertical stress would be at that depth Z in your soil mass, you simply calculate that by dividing the force that's carried by your foundation. So force is always in newtons, divided by the area or the increased area at a depth Z. So that increased area, you would have a footing, and your footing has a width of B and a length of L. Well, the increase in the width of your footing would be B plus Z, and also the same would apply for the length of your footing. The length of your footing also is increased by that depth Z. So to calculate your increase in vertical stress, you'll see in my answer key, I use a delta sigma B is equal to P, which is your force, divided by B plus Z times L plus Z. So if you're out in the field and someone wants to know what, the increase in vertical stress would be at a soil mass, and if that increase in vertical stress would be an issue, you could do this quick and dirty calculation and you would be able to provide that answer to the individual. So this is the approximate method. I'll go over how we do the calculation with the approximate method, but does anyone have any questions on the approximate method?
Generally, how do you know how deep you want to calculate it for?
It all depends. Generally, what we would do is we would take it to the center of your clay layer. So you could do it for sand as well. Generally, you're not going to have any bearing capacity issues or any issues with a sand material or a gravel material by applying that extra load, because your excess pore water pressures dissipate almost immediately. And clay and, sand and gravel material has a sufficient bearing capacity to carry that extra load. It's when you have that clay material or that silty clay material, it's not an overly strong material. And when you apply that excess or that extra load, that extra pore water pressure takes a long time to dissipate. So there's the potential that you could cause your foundation material to fail. So generally you would calculate your increase in vertical stress at the center of that clay layer, or if you have another layer of concern, that's where you would calculate it.
Okay.
So I'm going to switch over to my IP though. Okay, now I can't tell if you guys can hear me, because it sounds like my sound's off.
I can hear you.
Okay, now it switched to my computer. Okay, went off of my AirPods to my computer. Well, whatever. We'll just go with it. Okay. I'm hoping you guys can see my screen still. I tried to switch my IPvo so it doesn't do that zooming in and zooming out feature anymore. So I think the clarity is good. Okay. So example problem 410 would be an example where we would use the approximate method. So with this method, or with this question, I'm stating there's a 3 meter by 4 meter rectangular area, and it's loaded with a uniform load of 250 kPa. And it's saying use the approximate method, or using the approximate method, what is the increase in vertical stress due to this load at a depth of 3 meters? So you'll see over here, I drew my rectangular foundation. Its width would be 3 meters and its length would be 4 meters. Always just assume your width is your smaller dimension, so that B always represents your smaller dimension. So in this example problem here, B would be equal to 3 meters and your length would be equal to 4 meters. In the end, it wouldn't matter, but when you get into foundation design, B always represents our smallest dimension. So I figure at this stage it's just easier to go with the rule of thumb that you would that you would use when you're doing foundation design. So we were given a uniform load of 250 kPa. So we know that our approximate method formula is our increase in vertical stress. So delta represents our change in or our increase in vertical stress. So delta sigma V is equal to P, which is our load, divided by B plus Z times L plus Z. Well, we know that P is a load in newtons, and we were given an increase in, or sorry, a load in kPa, or that load actually represents a stress. So we know that to convert a stress to a load in newtons, we would multiply our load that was given in kPa by the area of the foundation. So we know the dimensions of our foundation are 3 meters by 4 meters. So to calculate our load in newtons, we would go P is equal to 250 kPa, or 250 kilonewtons per meter squared, times 3 meters times 4 meters. So P is equal to 3,000 kilonewtons. So now I have all the information that I need to be able to go back and use this approximate method formula. So I have my p-value, and my p-value is 3,000 kilonewtons, and I'll divide that by b plus z. So I know b is equal to 3 meters, and I know that z is equal to 3.5 meters. And the 3.5 meters would always be given to you in the problem, so you don't have to determine what depth you're going to calculate this increase in vertical stress at. And you would always be given your area of your rectangular area or square area, so your foundation area, that would always be provided to you. And your load in either kPa or in kilonewtons would be provided to you as well. So we have B plus Z, so 3 plus 3.5, and then L plus Z, so that would be 4 plus 3.5. So if we go through and do that calculation, we can determine that our increase in vertical stress, so delta sigma V, or our change in vertical stress, is equal to 61.5 kPa. So if we were to look at this foundation area at a depth of 3.5 meters below the base of this rectangular foundation, I would have an extra stress associated with this load of 61.5 kPa. And that increase in vertical stress, I would add to my overburden stress, which would be my initial stress, to calculate what my final stress would be. And that's what we're going to work on Friday or tomorrow, I guess. But for right now, the only process that you need to sort of work through is to determine what your increase in vertical stress would be. So you know that your increase in vertical stress for this example is 61.5 kPa. I'm going to pause there to see if anyone has any questions.
Should the difference in vertical stress always be rounded to 0.1, or is it?
I always round it to 0.1.
Okay.
Yeah. There must be other questions. No other questions? Has anyone worked through these? Okay. You guys are quiet today. Okay, if there aren't any questions about the approximate method, I'm going to move on to the influence coefficient method. I'm always here if you have questions when you start to work through the problems and there's something that doesn't make sense, don't hesitate to reach out to me. I'm always happy to answer the questions. Again, you can also review the material that I'm not going over. It's just that I'm just trying to highlight what would be really important for you on the next test and what methodologies we typically use when we're calculating settlement in a clay layer. So the other commonly used method is called the influence coefficient method. And we use the influence coefficient method for rectangular, square, or circular footings. So using this method, we also want to calculate our increase in vertical stress below a loaded footing area. And we can calculate it by using this formula here. So our increase in vertical stress, so delta sigma V is equal to our force, which is P, divided by the footing area, which is A. So if it's a rectangle, it would be B times L. If it's a circular area, it would be pi R squared. And then that's multiplied by IC. And IC is our influence coefficient value. And there's various tables we use to determine what this influence coefficient value is. And I'll show you guys how to use those tables today. You can also calculate your increase in vertical stress by multiplying your uniform pressure, which is Q, times your influence coefficient value. You'll see these two equations are actually the same because P divided by A is actually your Q value. So these two equations are in essence stating the same thing. I'm not going to go over example problem 411. I think I have a detailed solution for that, and the tables are provided, so you guys can work through that yourself. I'm going to go over how you use the influence coefficients tables to calculate the stress below the corner of a rectangular square footing and below the center of a rectangular or square footing. Again, it's the same methodology where your increase in vertical stress. So if we're going to look at calculating our stress below the corner of a rectangular or square footing, we would use the same equation. So delta sigma V is equal to our load divided by the area of our foundation. So for a rectangle, it would be B times L. And if it was a square, it would just be B squared times IC, which is our influence coefficient. We use a table to calculate or determine what our influence coefficient is. This table here is just a snippet of the table that you would use. If you look at your example problems, and sorry, they're probably labeled as example problems from chapter 4. At the back of those example problems and also on your course notes equation sheet, there are tables of your influence coefficients that you would use to do the calculations. And I'll use those tables today and show you how to use those tables. To determine your influence coefficient, you have to calculate something called your M value, which is you determine what your M value is by dividing the width of your foundation divided by Z. And Z again represents the depth in your soil mass in which you are interested in calculating your increase in vertical stress, and your N value. And your N value is represented by the length of your footing divided by your Z value as well. And if you know your N value and your M value, you can determine your influence coefficient by using a table. There is a really long formula that you can use to calculate what your influence coefficient would be. I'll show that equation to you right here. But that influence coefficient is much easier. It's just much easier to determine it using the table. So I'm going to work through example problem 412. Are you guys okay with me working through the example problems, or is there anything specific you want me to work through on this chapter for you guys? Yes, please. Okay, work through the example problems. Okay, so example problem 412, it's asking you to calculate or find the increase in vertical stress at a depth of 4 meters under the corner of a 2 meter by 4 meter rectangular footing carrying a load of 4,500 kilonewtons. So in this example problem here, the width of your footing is 2 meters and the length of your footing is 4 meters. You know you want to calculate what your increase in vertical stress would be at a depth of 4 meters below the base of your footing. And you know that your footing is carrying a load of 4,500 kilonewtons. So the first step that you would do is to calculate what your influence coefficient would be. So to calculate your influence coefficient, you need to calculate what your M value is and what your N value is. So in this problem here, M would be equal to B divided by Z, and M is always equal to B divided by Z. So in this problem here, your B value is 2 meters, so it's the smaller dimension of your footing, and your depth of interest is 4 meters. So 2 divided by 4 is 0.5. And you would also want to calculate your N value, and N is equal to the length of your footing divided by your depth below the footing at which you want to calculate your increase in vertical stress. So in this instance, it would be 4 meters divided by 4 meters, which is equal to 1. So your M value and your N values are dimensionless. They don't have any units associated with them. So now I'm going to switch over to this fancy dancy table. Get rid of this one. Okay, so we know our M value is 0.5. So if you look at this table right here, this is your influence coefficient table. You'll see M is here and N is along the top. So these values down, which would represent a column, are represented by your M values. And your N values here are represented by these values that are provided along this row here. So our M is equal to 0.5. So we know our M value is equal to 0.5. So I always draw a line horizontally from our M value of 0.5. I know my N value is 1. So I know my N value here is 1. So I'm going to draw a vertical line down. And where my horizontal line from my M, I guess we'll call it a row, this M row, and my vertical line from my N column intercept, this is my influence coefficient value. So you'll see here that my M and N lines intercept at this value of 0.1202. So the point in which these two values intercept is my influence coefficient. So that's how I determined what my influence coefficient value is. So I'm going to pause here to make sure that it's very clear how we use this chart, because if you can't use the chart, it's not possible to calculate the influence coefficient values. Does anyone have any questions on how you determine the influence coefficient value? Makes sense.
So if you got a value in between 1 and 1.4 for your end value, is it like a linear difference between the two? So you calculate it, or you just pick the highest one?
No, you do your interpolation, and you just have to assume it's linear.
Alrighty.
I try not to give values such that you have to do the interpretation. Or if you do have to do interpretation, it's pretty easy interpretation.
Alrighty.
But I try to give values on a test that you're able to easily determine from the table. But say, for example, you had an M value of 0.5 and an N value of 1.2, you would just take the average here. So you'll see that your IC value at 1 would be 0.1202, and at 1.4 it would be 0.13. So if you had an N value of 1.2, I would just average these two values and say that that is what my IC value is. Does that make sense, Sean?
Yeah, that makes sense.
Okay. Anyone else have any questions about using the chart? No. Okay.
Alina,
Yes.
so let's say if the numbers are not there, let's say for M, it's not there. Let's say 0 point something, 0.5 something, and it's not in the table exactly. Do we round up or do we round down?
I'll never give you anything where it doesn't, where it's not on the table.
Okay.
Yeah, you would just do an interpolation sort of between the two values. So hopefully your N value is on the table. And if it was, then you would just do an interpolation between the 0.5 and the 0.6 value.
Sounds good.
But in all honesty, if we were doing design and that was the case, we would take the most conservative number. So we would take the highest value for IC. So that's what we would do in the design process if we were unsure of something, just to be conservative. Okay, so back to example problem 412. We calculated our IC value to be 0.1202. We would use this formula here. Our increase in vertical stress is equal to our load divided by our foundation area, which is B times L. So IC is equal to 4,500 kilonewtons. That was provided in the problem, divided by 2 meters, which represents our B value, and 4 meters, which represents our L value. And then we multiply this by our influence coefficient, which is IC, which is 0.1202 in this case. And we were able to calculate that our increase in vertical stress was 67.6 kPa. Anyone have any questions on how we calculated this value? Guaranteed you'll have to do this next week on your test. So if it doesn't make sense, please ask questions now. Okay, we're still going to continue working with influence coefficients, but now, yes, so this replaces the B plus Z, L plus Z in the other method. So the approximate method uses this equation here, Clive. So this delta sigma V is equal to P divided by your area. So if you look at the approximate method, the P divided by B times L is the same as the influence coefficient, but it's this plus Z that sort of differentiates the two methods. You get fairly close values, or fairly close, values for your, when you're calculating your increase in vertical stress using the two methods, but they are, but there is slight differences in them. So. Okay, so stress under the center of a footing. So if you're looking at calculating the stress under the center of a footing, it's the same as adding together the stresses under the corner of 4 footings. And these footings would have half the width and half the length. And then each of these footings would be carrying a quarter of the total load. So I'll work through an example problem with this, but think of it in the sense of, imagine if we had a footing and it had a dimension of B times L, and I asked you to calculate the increase in vertical stress at the corner. You would just follow that methodology that we just worked through. Well, now I'm going to ask you to calculate what the increase in vertical stress would be under the center of a footing. So the methodology is slightly different. So what you need to do is divide your rectangular footing, or it could be a square footing, into 4 equal rectangles or 4 equal squares. So you divide that into those squares or the rectangles, and then you're looking at determining the increase in vertical stress at the corner of each of these 4 smaller sized rectangles. So that way you're able to use the same methodology as we used previously, because you are calculating the increase in vertical stress under the corner of these, or sorry, under the corner of each of these smaller footings. And you can follow the same process and methodology to determine your influence coefficient. The one thing to note when you are looking at calculating the increase in vertical stress under the corner of each of these 4 smaller footings, you have a total load that's applied to your foundation area. But when you divide it into these 4 smaller rectangles, your total load that's being applied to each of those 4 individual corners is a quarter of the total load that's being applied, because each of those corners is taking a quarter of the load. So the load that's provided to you in the problem, you would divide it by 4, and that's the load that's being applied to the corner of one of those smaller rectangles. Anyone have any questions? So usually when you're dividing your rectangular or square load into 4 equal sized rectangles or squares, the dimensions are always 1/2 B and 1/2 L for these smaller rectangles. Anyone have any questions on sort of the theory behind why we're doing this when we're calculating the increase in vertical stress at the center? No? Okay, well, let's work through an example. What's the word or the? Okay, the word that you're looking for to know that you need to divide it into the 4 equal parts is if I'm asking you to calculate the increase in vertical stress at the center of the footing. So if I ask you to calculate it at the center, you know that you need to divide your footing area into those 4 equal rectangles or squares. And can I explain the reason why we have to do that? Because the influence coefficient method doesn't work when we're asking you to calculate the increase in vertical stress under the center of footing. But if we divide our footing into 4 equal rectangles or squares, then those smaller rectangles you'll see as represented by these red dots here, we're actually calculating the increase in vertical stress at the corner of those 4 smaller footings. So then we can use the influence coefficient method. And once we calculate the increase in vertical, it generally works for rectangles and squares. You would use another formula for circles. And those are provided in the notes, like the class notes. But the influence coefficient method works for, this table that we're using works for rectangles and squares. There's another table that works for circles. And you can calculate your influence coefficient for circles under the center, the edge, or an average. But it's a different table. So this table we're using only applies to rectangles and squares. Okay, this example problem here, 413, is asking you to find the increase in vertical stress 1 meter below the center of a 4 meter wide by 3 meter long rectangular footing if the load on the footing is 3,500 kilonewtons. So the key word here is center. So when I'm asking you to calculate the increase in vertical stress below the center, you know you have to divide your footing shape into 4 equal size shapes. So either 4 equal size rectangles or 4 equal size squares. So that's the key word that you would look for here, and that's why it's underlined. Your footing shape is 4 meters by 3 meters long, and the load is 3,500 kilonewtons. So again, we start out with calculating our M and N value. So when I drew out the problem here, I drew it out so that I have a 3 meter wide by 4 meter long rectangle. I've divided this rectangle into 4 equal sized rectangles. So the length of my rectangle is 4 meters. So when I draw 4 equal sized rectangles, my new rectangles are 2 meters long. My initial rectangular footing was 3 meters wide. When I divide that or make it into 4 equal sized rectangles, my width of my rectangular footing right there now becomes 1.5 meters. So the width of each of these individual rectangles is 1.5 meters and the length is 2 meters. And so I'm looking at calculating the increase in vertical stress at this location here, this location, this location, and this location. So I'm calculating my increase in vertical stress at the corner of each of these 4 smaller sized rectangles. So now when I'm going through to calculate my M and my N value, the width of my footing is no longer, of my rectangles are no longer 3 meters, they're actually 1/2 times the initial width because I have these 4 smaller sized rectangles. So when I'm calculating M is equal to 1/2 times B divided by Z. Z in the problem was given and Z is 1, and 1/2 of our B value is 1.5. So my M value is 1.5 divided by 1, so that's equal to 1.5. N value is the same. The initial length of my footing was 4 meters, but I divided it into 4 smaller rectangles. So the new width of my smaller rectangle is 2 meters. And again, my depth Z is 1, so 2 divided by 1 is 2. So I know my M value is 1.5 and my N value is 2. So if I go to my handy dandy table again, I know that my N value is 2. So I will draw a line down and I know my N value is 1.5. So this is my N value, M value of 1.5, and my N value is 2. Well, these two lines intersect at this value of 0.2236. So that value there represents my IC value for this scenario. So I know that my IC value for this scenario is 0.2236. Okay, the next step is I would look at my p-value for these 4 smaller sized footings. So I know my original p-value that is applied, or the original load that's applied to my footing is 3,500 kilonewtons. But in this instance here, as I indicated, you're applying a load to the corner of each of these 4 smaller rectangles. And the original load that's being applied, even though it's 3,500 kilonewtons, 3,500 kilonewtons isn't being applied to the corner of those 4 smaller footings. A quarter of the 3,500 kilonewtons load is being applied to those corners of the footing. So each of those smaller footings have a load of 875 kilonewtons that's being applied to the corner. And if you were to sum up the 875 kilonewton load that's being applied to each of those 4 corners, that represents your total load value of 3,500 kilonewtons. So I'm going to pause there and provide you guys with an opportunity to ask questions about the process so far. No questions? Okay. So again, we use this formula here to calculate our increase in vertical stress. So delta sigma V is equal to our load divided by our foundation area times IC. So in this instance here, we know our load is 875 kilonewtons at the corner of each of these smaller rectangular footings. We know the area, or our B value and our L value, are decreased because we've divided our larger footing into 4 equally sized smaller footings. So we know the length of our smaller footing is 2 meters, and we know the width of our smaller footing is 1.5 meters. We know our influence coefficient value, IC, is this value here of 0.2236. And then the other thing that I've included in this is a value of 4. So we're multiplying all of this by 4. And the reason why we're doing that is if we just calculated this value right here, this value right here represents the increase in vertical stress at the corner of one of those smaller footings. But you want to determine what the increase in vertical stress would be at the corner of each of those 4 smaller footings, because that represents the total increase in vertical stress at the center of the larger footing. So you could calculate this value right here without multiplying it by 4, but then you have to sum it 4 times to represent the increase in vertical stress at the center of the footing. So I just multiplied it by 4, so I didn't do the actual summation. I just find it easier that way. If that doesn't make sense to you, you can calculate it this way and then add it 4 times to determine what the total increase in vertical stress would be at the center. So this 4 here represents the 4 smaller footings. So that's why I've multiplied it by 4 to get the increase in vertical stress at the center of the larger footing.
Could you just do 3,500 divided by 2 times 1.5?
Yeah. Because in essence, you're going to get the same answer.
Okay. Would it be wrong if we did that on a quiz?
Nope.
Okay.
Yes, I just sort of broke it down by process to sort of hopefully demonstrate why we use this methodology and why we use it in the way that we do. But Sean, if you did it that way, it's not wrong.
Like the way you made it, like you wrote it out, makes a lot more sense than if I was to just write 3,500 divided by 2 times 1.5. But
Yeah.
yeah.
Elena, what's the, could you explain the why you multiplied by 4 again for the small footage?
Yeah, the reason why I multiplied by 4, Saywan, is because when I did this calculation here, so when I went the 875 divided by the dimensions of the smaller footings, and then multiplied by our influence coefficient value, that just represents your increase in vertical stress at the corner of one of those smaller footings. But the question is asking you, what is the increase in vertical stress at the center of that larger footing? So if we were to take a look at our footing here, you only calculated the increase in vertical stress at that location there. So that's just the increase in vertical stress at the corner of one of those footings, but it doesn't represent the total increase in vertical stress. So you also need to know what the increase in vertical stress is at that location, for that footing, for this smaller footing here, and this smaller footing here. So you'll see that I'm multiplying by 4 so that I can determine what the total increase in vertical stress is at the center. Because otherwise you're just calculating what the increase in vertical stress is at the corner of one of the smaller footings. But you need to know what the increase in vertical stress is at the corner of all 4 of those smaller footings.
That
That's
makes
why I multiplied by 4.
Thank you.
Does that make sense now, Saywan?
Yes, it does actually make sense right now. Thank you.
Okay, perfect.
Another question, probably more unrelated, but if we had an irregularly shaped foundation, are we going to be going through that in this course, or is that kind of beyond?
No, and you wouldn't even do this in a foundation design course in university. They don't give irregularly shaped foundations because it makes life hard. Generally, we just assume it's rectangular or square. Even like hexagonal or octagonal foundations, they're quite rare, but you just assume they're circular.
Okay.
So they'll always be square or rectangular in this course. Obviously, I've given you the skill set. If you had a line load or a point load, or if they're circular, you're able to calculate your increase in vertical stress, but we're more concentrating on square or rectangular footings.
Okay.
So Conrad was asking about circular foundations. I believe example problem 411 works through a problem where we're asking you to calculate the increase in vertical stress below the center of a circular footing and below the edge of a circular footing. This is the table right here that you would use to calculate or determine, you don't have to calculate, you just have to determine what your influence coefficient would be for a circular footing. So this represents for a circular footing. And you'll see here, the only component you need to determine is your Z over R value. So Z represents the depth below the base of the footing, and R represents the radius of your footing. So obviously, if your footing is circular, you would have a radius that you're able to use, and the depth below the base of the footing would be provided as well. So if someone asked you to calculate it below the center, say at a Z over R value that was determined to be 2.5, you would know that your influence coefficient below the center would be 0.2. Your influence coefficient at the edge of the footing would be 0.151, and the average value is 0.174. So you would just use this table. So there's different tables depending on what your footing shape is.
And what do you use the average one for?
Generally we wouldn't. Generally we would just use under the center. because you always experience the greatest amount of settlement under the center of your footing, especially flexible footings, which most footings are designed to be flexible. So we generally use under the center. I guess if you wanted a representative of what your settlement would be on average between the center and your edge, you would use the average. But we're pretty conservative in design, and we would generally take under the center of the footing because that's our largest, where the largest amount of settlement would occur.
All right.
Do you guys want me to go through any other problems like 414? Or do you guys want to get on to supervisory management? I'm open. What do you guys think? Anyone? Does this give you a good foundation? Strip footings are slightly different in the sense that you would divide them into your 4 equally shaped footings. So under the center of the footing, it's still exactly the same as how it would be for a rectangular or a square footing. The difference comes when you're calculating the increase in vertical stress under the edge or under the corner of the footing. So if we look at this example problem here, the first one, A, is we calculated it under the center. So you'll see I followed the exact same methodology as I did for the rectangular footing, where I divided it into 4 equally sized shapes. And I went through and I calculated my M and my N value and followed the same process. If you look at it, at calculating the stress under the edge or under the corner of the strip footing, it is different than a rectangular or square footing. In this instance, you divide your strip footing into 2 equally sized shapes. So obviously when something's a strip footing, it's sort of infinite in length. So that's not going to change. Even if you divide it into 2 or 4 equally sized shapes, infinity is still infinity. In this instance here, we had a strip footing, and the strip footing is 2 meters wide. So the width of our strip footing is 2 meters, and the dimension L is infinity. So in this instance here, even when I divide it into 2 equally sized rectangles, when I'm calculating my M value, M is equal to B divided by Z, and B is still 2 meters, even though I've divided it into 2 equally sized rectangles, and Z, the depth below the base of my footing, is still 2 meters. And my L value, even when I take 1/2 of my L value, L was infinity, so half of infinity is still infinity. So my N value is still infinity. The difference is when you're calculating your increase in total stress. So you'll see here, the process is still the same. I determined what my IC value was. I know what my stress that was applied to the area was, and it was 75 kPa. The difference is I'm multiplying by 2 in this scenario, whereas if I had a rectangular or square footing, I wouldn't be multiplying by 2. And that's because I didn't have to divide my rectangular or my square footing into 2 equally sized rectangles or squares. I could just keep it as is. So that's sort of the nuance or the slight difference with a strip footing compared to a rectangular or square footing. And that's because you're calculating your increase in vertical stress at the corner of the footing 1 at this location and the corner of footing 2 at that location. So it's just the summation of the increase in vertical stress at the corner of those 2 equally sized smaller footings. for a strip footing. So the process is the same. There's just slight nuances or differences in the process.
And what would be like the length where it would go from length to infinity?
Sorry, Sean, what do you mean by that?
Well, like if your footing was 10 meters long, would you consider that infinity, or would you consider that 10 meters versus like 50
Usually
meters?
we'll have a ratio. So if your footing width is say 2 meters and say your footing length was 20 meters, at that point, you would almost consider it infinity.
Mhm.
So usually at least 10 times greater than your footing width, then at that point, we would say it's classify it more as infinity or a strip footing.
Yeah. Okay.
Okay, anyone else have any other questions? Does this help you guys? Does this clarify any questions when you guys were working through the problems? Okay, well, I'll let you guys go for the day. So tomorrow the plan is we're going to work on our consolidation chapter. So we're going to calculate what settlement would be for our clay layers based on if our clay is normally consolidated or over consolidated. So we'll have problems where we're looking at what is our increase in vertical stress and what is the settlement associated with adding that that stress to the foundation area. So we'll work through that tomorrow, and we're also going to look at how long does it take for settlement to occur, or how long does it take for 100% of our settlement to occur, or certain percentages of our settlement. So it'll be a settlement sort of versus time discussion. So that's the plan for tomorrow. So we're going to use the skill sets that we've developed today with our external loads chapter, and we're going to apply those as well to our settlement calculation unit. So come prepared. It will probably be a 3-hour class tomorrow, but we'll work through quite a few example problems. So I think it will be a great class. It's also an important class in the sense that we'll work on determining there's different formulas that you use for calculating settlement based on your soil conditions. So we'll work through the process of determining which equation applies to the different scenarios that we're evaluating. I will record tomorrow's class, so if you're busy, you can view the recording after. So anyways, have a great day, guys. I'm always here to help. So if you have any questions about what we discussed today, I am available today to answer those questions. Otherwise, have a good day. Shoot, I think I forgot to record.
Lena,
Yes, Joe.
quiz stuff is on chapter 11, right? Like the lab stuff?
Yes.
Okay, so just, it's mostly like from the labs more than the notes, or it's
For tomorrow's class or the class that we just had?
the lab that's due at 5. I just haven't written
Oh,
it yet.
yes, it's completely on your lab notes.
Okay.
So completely on the work from like chapter 6 of your lab notes. That being said, it's more concentrated on the material that I provided for the lab. So in the sense of, can you determine like from a plot of void ratio versus log vertical stress? Can you calculate your pre-consolidation factor, a CC value, a CR value, like those sort of parameters is what we're looking at from the lab, and a couple theory questions as well.
Okay.
So it's more focused on the actual consolidation lab than it is from the theory that we've been reviewing in class.
Okay,
Those
thank you.
calculations will be on the test next week.
Okay, thanks.
Yeah, no problem. Do you have a question, Emmanuel?